Hello, dear students. In previous 2-3 lectures, we are learning the integral calculus, and in integral calculus, we learn reduction formulas, gamma function. And today, we are going to learn one more important point, that is beta function. That is beta function. Now, beta function is also one of the important application to evaluate the integral, which has complicated integrands or infinitely integrable functions, then we can easily convert them into solvable by using beta function. First of all, we have to understand what is meant by beta function, how beta function is defined, and how that beta function will compare with converting the integral into the solvable form. Now, again, the function, I'll write first the definition of this gamma function. What is different? Just to show you. Here, the integral I equal to integral 0 to 1 x raised to m minus 1 1 minus x raised to n minus 1 dx. Here both m and n are positive integers, and this integral we call it as beta mn, and denoted by the symbol beta mn. Beta mn equal to integral 0 to 1 x raised to m minus 1 and 1 minus x raised to n minus 1 dx. Here you observe that the given integral containing these two terms, x power whose power is m minus 1, and 1 minus x term is complement of literary complement of x, the 1 minus x whose power is n minus 1. Now, if integrand with limits 0 to 1, you can check here limits for the beta function is 0 to 1, and gamma function we have 0 to infinity, and in gamma function we have exponential function e raised to power of power, and this is one of the simplest method to identify beta function in the form of x and 1 minus x form. One term is x, second term is 1 minus x, and this is our formula for beta function. We can say it's a definition also. Now we move to next point, that is, so there are some properties of the beta function. We call it as properties also. Properties of the beta function. Now, which are the properties and how we are going to use? I'll first define which are the properties, and I'll go afterwards how to use these properties. Now, the role of m and n in the beta function are commutative properties. That's key material where m is where n is there. The beta mn is same as beta n em. That is meaning here commutative property in the m and n. Now, second important property you can check. Beta function can also convert it into gamma form. That is beta mn equal to gamma m into gamma n upon gamma of m plus n. Gamma of m plus n means this is the important property. You can convert the gamma function into beta function and beta into gamma function. Now, the third property, the beta function also can be converted into trigonometric function form. Trigonometric function beta mn in terms of trigonometric function can be written as 2 times integral 0 to pi by 2 sine theta raised to 2m minus 1 and cos raised to 2n minus 1 theta d theta. Means this is also one of the beautiful formula. You can say also you can convert these reduction formulas also in terms of beta function. Okay, they are relation between beta, gamma, and function. This gives to you the beauty of the integral calculus, how we are going to learn and how to convert them into integral soluble form. Now this same formula is written in the different way by integral formulas. Means integral 0 to pi by 2, 0 to pi by 2, sin raised to m x, cos raised to n x dx. Means according to our reduction formulas, sin raised to m, cos raised to n can be converted into beta function, that is 1 upon 2 beta of m plus 1 upon 2 n plus 1 upon 2. This is an important property of conversion of, and this formula also can be converted into gamma function. Here is equal to 1 by 2 gamma of m plus 1 upon 2, again gamma of n plus 1 upon 2 divided by sum of these two, that is m plus 1 upon 2 plus n plus 1 upon 2. Therefore m plus n plus 2 upon 2, you get this formula. Means this is the most important formula which shows a relation between reduction formulas, beta function and gamma function. Means any examples you can convert into reduction formulas, reduction into beta, beta into gamma function. This some standard integrals, you can use this technique and you can solve the examples respective to the which under the which conditions it will be solvable. Then you can get easiness. If you have so many tricks or formulas, then you can get easiness for the solving the examples. Now same the reduction formulas of sine trigonometric functions you can get on here. Integral 0 to pi by 2 sin raised to n theta d theta as written as 1 by 2. Now here n you put 0 here, n you put 0 and m you put n, you get here 1 by 2 gamma of n plus 1 upon 2, and here gamma of 1 by 2 divided by, once you understood one formula, that formula number 4, then the remaining all the formulas you can obtain by using that formulas. Now this you get, means this is important relation formulas for all the examples. Now here you put n equal to 0 and m equal to n, you get integral formulas here. And if you want cos formula, put cos here as it is and m equal to, put 1 here, you get the cos formula. Like that we have so many such properties where you can get the integral formulas. Just I'll show you next one important property, property number 7. Now here is integral 0 to infinity x raised to m minus 1 upon 1 plus x raised to m plus n dx. This integral, you can see here x raised to m minus 1 is there and 1 upon 1 plus x. The standard formula we have x raised to m minus n into 1 minus x raised to n minus 1. But if you see this formula here, you get 1 plus x formula also there here. This can be written as again beta m n, beta m n. Means this number added by 1 here and this whole number subtracted by n. This m you subtract, you get number. This number is subtracted by m, you get number. This is one of the best property or important property also, which you can say. Now next property, property number 7, we have integral. This is very important property. Integral a to b, means general interval integral a to b x minus a raised to m b minus x raised to n dx. This is written as this is equal to right here b minus a means these two numerical values a and b raised to m plus n plus 1 into beta m plus 1 and n plus 1. This is the important formula, one more formula. And this formula number 6 again modified into general formula that also can say one more property. Then here integral 0 to infinity x raised to m minus 1 upon a plus bx raised to m plus n dx is equal to 1 upon a raised to n b raised to m into beta m n. So here put a equal to 1, b equal to 1, we get property number 6. Property number 6. So that there are standard properties that you can keep in mind. Here, this is important standard property, and from that you can get the any property you can solve by putting a equal to b equal to 1. Now, one is, there are some additionally formulas properties also you can say. There are some properties here. Beta mn, I'll take a different one. Beta mn also can written as the sum of two beta functions, that is beta m plus n plus 1 and plus beta m plus 1 and n. Sum of two beta function. Beta function can be written as sum of two beta functions. Now we'll move to next slide. Now these are the important properties, and these properties we are going to use while solving the examples. Now one more important property that just I'll explain you, that is important for the concept to understand the beta function. Now, whenever we have any types of examples, at time this property is going to use. You can say substitution also how to substitute. Integral 0 to 2a, integral 0 to 2a x into root 2a x minus x square dx. This is like example only, but by using this simple concept, now our target is here to convert integrand x raised to m minus 1 and 1 minus x raised to n minus 1 dx. Now here 2a is there, x is there, and here also x is there. You can take one x also from outside. But what to be substitute here, x square plus, when you get this whole is 1 and this is here x only. Means that like you substitute, means here if you replace x equal to 2at, x equal to 2at, then our integrand becomes the standard form. Then here 280 means here this is the substitution. What you have to substitute? This part, whole part is replaced by with the parameter, and that is the one simple technique to solve it. Now we go for some examples, standard examples, how to utilize these properties to get the solution for the integrals which are comes under the beta function. We'll see example 1. Take example 1. One example. First one. Suppose evaluate integral I last you integral 3 to 7 x minus 3 raised to 1 by 4 7 minus x raised to 1 by 4 into dx. Now we learned as important property that properties belongs to. But suppose if you will not remember the property, then how to convert this integral into a soluble form? Then I'll say integral I equal to. So first read it properly. 3 to 7 x minus 3 raised to 1 by 4, 7 minus x raised to 1 by 4 dx. In such cases, how to substitute? Here 4t plus 3 means difference between these two. Difference between these two. If or difference between this is limit here. This 3 also here, this also here. Means the difference between these two. You get plus 3, the first part. You put this parameter equal to x. This parameter equal to x definitely. As x equal to x minus 3 upon 4 equal to t. T equal to x minus 3 upon 4. This is one of our substitution. Now after substitution we go for the change of their limits. What value of x we get and what value of t has to get by substitution. Now as x tends to 3, x tends to 3, then t becomes 3 minus 3, t becomes 0. And x tends to 7, then 7 minus 3, you get 4, 4 upon 4 is 1. That is nothing but here difference between these two limits and that numbers. By doing this one, we get the change. Now, to differentiation 4 dt equal to dx. Therefore, dx equal to 4 dt. Now, change the limits. So, integral I is equal to integral I equal to. Now, limits now, new limits here 0 to 1. 0 to 1. Then put here x equal to this number means here integral 4t plus 3 minus 3 raised to 1 by 4 plus 7 minus 4t minus 3 raised to 1 by 4. Now dx is replaced by 4 dt. Here is dx value. Dx is replaced by 4 dt. Now simplify this integral. Integral I equal to. Now terms you can simplify it. I'll use here different sketch for the understanding. Here 0 to 1 as it is. 4 this that cancels. 4 raised to 4t raised to 1 by 4. And here 7 minus 3 we get 4. 4 minus 4 means again I'll take here 4 common outside. Write 1 minus t raised to 1 by 4. And for this also we get right 1 by 4. Any number bracket we are taking outside. With index also we can take outside. Into 4 into dt. Now here see 4 how many times are there? At all the times you have to take outside. Here 4 is to 1 by 4. One time see there 4 is to 1 by 4. One more time here 1 by 4 there means 1 upon 1 by 4 again. And here is 1 by 4. Then that index is 1. Then index will is powers of all 4s. Integral 0 to 1 t raised to 1 by 4 into 1 minus t raised to 1 by 4 dt. This is numerical number value and this becomes a beta standard form, beta function form. And here to add these numbers, we get a values. I'll use again a different sketch for the to understand the concept. Now here the bit function I integral I equal to that 4 raised to here LCM we will take here multiply 4 and divide by 4. 4, 5, 6, 6 upon get 4, 6 upon 4. 6 upon 4 means 3 upon 2. 3 upon 2 for the power of 4. Integral 0 to 1 here beta function. Now you have to use here beta. This 1 by 4 plus 1. 1 by 4 plus 1 means 5 by 4. You get 5 by 4. 5 by 4 comma Here again this you add by 1 and you get again 5 by 4. This is beta. 4 raised to 3 by 2 means root of 4 is 2, 2 raised to 3 means 8, 8 into, this becomes 8 into beta 5 by 2, 5 by 2. This is the way to calculate. Then afterwards you can use the formula. Then 5 by 2 in terms of gamma function, you get the values. This is the simplest way to convert complicated integrals or the uh, functions of functions integrals into the soluble form. Now we can go for one more example, then which covers one more property, any of the property. Then just to go for it. Now I'll take a standard example, which is very important for the so many types asked in exam and it containing so many applications. Integral 0 to infinity, integral 0 to infinity dx upon e raised to x plus e raised to minus x raised to n raised to n. This is an important example. Now such cases we have to use some substitution method or substitution to get the such integrals. Now suppose to take this given integral as I assume that is I equal to integral 0 to infinity. Now so many students get confused here. Here e raised to e also there, exponential powers are there, as well as integrals are 0 to infinity, and they get confused about this example is maybe soluble with the gamma. It's soluble with gamma also, but it get complicated. And if you use some substitution here, you get the simplest form. And this can be also written as 1 upon 2, 1 upon 2 integral minus infinity to plus infinity. Minus infinity to plus infinity. Inside I made here double times. Why? This function is even function. And dx upon e raised to x plus e raised to minus x raised to n. And you can put here such examples. You can put e raised to x equal to tan theta. E raised to x equal to tan theta. After this substitution, we get value of x and theta. X, if x is minus infinity, theta get 0. And x is plus infinity, theta will get 5 by 2. Therefore, examples will convert it into standard form. Now, by this substitution, e raised to x into dx, by differentiation both sides, we get sec square theta d theta. Therefore, dx equal to sec square theta d theta upon e raised to x. E raised to x means tan x. Upon e raised to x means tan x or tan theta. And by using this one, we'll get the integral I equal to, by substitution the limits 1 upon 2 or limits minus infinity plus infinity converted into 0 to pi by 2 by substitution pi by 2. Numerator get as x square theta upon tan theta with the dx value, then divided by tan theta plus 1 upon tan theta, and that is with cot theta raised to n d theta. Now again here sin cos tan is there, then convert them into also trigonometric functions for our simplicity, and we get integral 0 to pi by 2, 0 to pi by 2. For converting them into sin cos, numerator becomes 1 upon sin theta. 1 upon sin theta means cos square 1 upon cos square, and there tan you get 1 cos on numerator and sin get cancelled, cos get cancels. Then you get sin theta cos theta left out from the numerator, and here again if you convert into here, you get sin and here cos. Here sin theta plus cos theta Here you divide by, you get cos theta, and here you get sin theta, whole raised to n into d theta, and integral I equal to 1 by 2, integral 0 to pi by 2, 0 to pi by 2. Here if you cross multiply, you get sin square plus cos square to 1, and this cos into sin raised to n go to here, and you get a cos sin theta. Here you get sin theta, you get sin theta raised to, here is n and minus 1, this n minus 1. Same for cos theta raised to n minus 1, and you get here d theta, here d theta, and this is in the beta function formula, integral 1 upon 2, 0 to pi by 2, here sin raised to d theta cos raised to q theta d theta formula. Then we can convert this into a standard integral formula, convert into the beta function 1 by 2, then that would be converted into a functional form, beta properties, using beta property, and this becomes 1 by 2. This is already as it is there here, this value is here, it's a 1 by 2 into 1 by 2 beta p plus 1 upon 2 and q plus 1 upon 2. That formula we are going to use here. Now here one more times we have to take 1 by 2 for this formula, this integral. This integral we have to use the 1 by 2 again. 1 by 2 beta, beta means here this whole power plus means n power n, again here n upon 2, again n by 2, n by 2, and it becomes 1 by 4 beta n by 2, n by 2. This is the simplest to get solution for such examples. Now this is a, here only we have to get idea how to substitute when to put here. Just check it. E raised to x equal to 10. This is very important substitution. You have to substitute here. After substitution, you have to make, these are the such things, substitution. Then afterwards, change of limits, x and theta, change of limits, and that must be converted into a soluble or integral form. And like this you get, and this is also one of the important beta function properties, and that will solve here. Like this you can solve any types of beta functions by using the properties. Now we'll go for one more examples, simple examples, so where you can get these properties. I can go for one of the important example. The example is asked so many times in the exam. By using that property, integral 0 to infinity x raised to 8 1 minus x raised to 6 divided by 1 plus x raised to 24 raised to 24. Now such examples, how we are going to differentiate it. Sorry, this is here, plus to 6 here, into dx. Now how to convert them into soluble form or standard form. Now this I will treat it as beta function is integral I 0 to infinity. I multiply, this is not there yet. If I multiply 8 inside, this x raised to 8 minus x raised to 8 plus 6 at 14, you get 8 plus 6, you get 14 upon 1 plus x raised to 24 dx. Now here you get two different integrals split up into two integral form. Integral 0 to infinity x raised to 8 upon 1 plus x raised to here 24. This is one integral. Second integral minus sign, integral 0 to infinity x raised to 14 divided by 1 plus x raised to 24 dx. Now these two integrals you can solve simultaneously at a time with the standard formula. Then this can be written as integral 0 to infinity x raised to here 8 can be written as 9 minus 1 divided by 1 plus x raised to this you can write 9 plus remaining value 9 plus 15 dx, 9 plus 15 dx. Now 24 means if you subtract 9 from 24 you get 15, that is right as it is. Similarly for second integral also, integral 0 to infinity x raised to 14 plus 1 is 15, 15 minus 1 divided by that number you take here 1 plus x raised to 15 as it is, 24 minus 15 we get here number 9 dx. Then these two are the standard formula, and this you get, this is a beta 9915, that is beta mn minus this is beta 15 and 9 here 15 m is here 15 m is here 15 here m is 15 and here n is 9 and here m is 9 and n is 15. Therefore this two are. Now also we have one property, beta mn is same as beta n m. Therefore both are same, and these two 9 15 and 15 9 both are same. Therefore the answer will get 0. Answer will get 0. This is the simplest and important example. Here you can convert into that property. This is which property you applied here. We applied this important property. For property is that integral 0 to infinity x raised to m upon 1 plus x raised to m plus n dx is equal to beta m. Beta m. This is important formula which you use here in the solving these types of examples. Now we'll go for next one more examples. These examples are important for understanding the each property of the beta function. Each property of the beta function. I will go for next example. One more example. Now, if you evaluate integral 0 to 3, 0 to 3, x raised to 3 by 2, x raised to 3 by 2, upon 3 minus x raised to 1 by 2 dx, 1 by 2 dx. Now this example you can solve with different methods. So now I'm solving with here one of the important method. Here we can solve this example with by substituting here this x equal to some 3 into t. You can put x equal to 3t, x equal to 3t. You can solve this example just to solve in both method. Integral I equal to, if you put x equal to 3t, then dx equal to 3 dt, dx equal to 3 dt. Now check limits. As x tends to 0, x tends to 0, t also tends to 0. You put x equal to 0. Then x tends to 3, then t tends to, you put here 3, 3 equal to 3t is 1, 3 3 get cancels by t equal to 1. Then integral becomes integral 0 to 1, 0 to 1, 3t raised to 3 by 2, 3 by 2. Then divided by 3 minus 3t raised to 1 by 2 into in place of dx, but write 3 dt, 3 dt. And this example is equal to, now here all these take outside. Here 3 raised to 3 by 2 from the numerator one more, here 3 is there, that is equal to 1. Down you get, if you take common outside here 3, you get 3 raised to 1 minus 1 by 2. From the denominator also you get 3 common outside, and from that also you can get 1 3. Then integral the remaining part 0 to 1. Numerator is 3 raised to 3 by 2 is left out. Then denominator after taking 3 common outside, 3 raised to 1 by 2 common outside from the denominator, you get 1 minus t raised to 1 by 2. Here dt, here dt, and this is integral I equal to 3 raised to, if you make it here LCM, multiply 2 divided by 2, it's all are 2, and you get denominator here 2, numerator 3 plus 2 minus 1, 5 minus 1 is 4, 4 by 2, and this is beta. I'll write in standard form, integral 0 to 1, 0 to 1, t raised to 3 by 2, and 1 minus t raised to minus 1 by 2 dt, and this is equal to here 2 1 the 2, 2 to the 3 square, 3 cos square. Then this is here beta function, standard beta function equal to beta, this power index of this t you can add by 1, which you get 5 by 2, 5 by 2, and this index of so you can add by 1, you get 1 by 2, so beta 5 by 2 and 1 by 2. Then this you get 9 into beta 5 by 2 and 1 by 2. This is one of the method, and same example I'm solving with a different method in the next one slide. Now sometimes they ask you mention you separately, evaluate the integral by using this substitution 0 to 3 x raised to 3 by 2 upon 1 3 minus x raised to 1 by 2 dx, and then you mention you by putting x equal to 3 sine square theta, you have to solve this example. By substituting this one, you can solve the examples. Then you can see, you will go one by one, you will learn this concept how to get it. Already mentioned in the example, by using that substitution only you have to solve this example, not for your or own substitution. Then x raised to 3 by 2 upon 3 minus x into x raised to 1 by 2 into dx is x equal to 3 sine square theta. This is substitution. Then you can differentiate both sides. Dx equal to 2 3 are 6, 6 into sine theta, sine derivative again cos theta. This is 6 sine theta cos theta into d theta. You could differentiate this one. Now check about limits. This is very important concept here. We have to check limits of this function. As x tends to 0, x tends to 0, it also tends to 0. Then x tends to 3, x tends to 3, you put here 3, 3 equal to 3, 3 equal to 3. If they get cancelled, sine square equal to 1. Sine square equal to 1 is possible only for 90 degree. Therefore, theta equal to 5 by 2. And now integral becomes, integral I becomes, now new limits of this integral 0 to 5 by 2. 0 to 5 by 2. And x here, this one value, x you put here 3 sine square theta raised to 3 by 2, raised to 3 by 2, and divided by here 3 minus 3 sine square theta, 3 minus 3 sine square theta raised to 1 by 2 into d theta. D theta is here to hold 6 into sine cos d theta, sine cos d theta. That is, I'll simplify in the next line. Integral equal to, from here we could take 3 outside, 3 raised to 3 means here 3 raised to 3 by 2, constant will take outside integral sign, 3 raised to 3 by 2, and here down you can take the outside common also, get 1 upon 3 raised to half to get outside, and that index will get 3 raised to 3 by 2 minus 1 by 2. All the remaining parts again into 6 is also constant will take outside from here. Then integral left out part 0, 2 pi by 2 sine raised to, here square is there, here root is there, means that cancels, 3 theta upon, here after taking outside 3 common, 1 minus sine square, get cos square, 1 minus sine square, get cos square root, you get again cos theta into sin theta cos theta d theta, sin theta cos theta d theta, and after this all the calculations, then you get this side cos get cancels, sin becomes 4, and here this integral becomes I 3 raised to, then here 2 3 raised to 2 minus, it's here 3 minus 1 2, 2 upon 2 is 1, 3 raised to 1 into 6, and this integral 0 to pi by 2 sin raised to 4 theta d theta. You can use the reduction formula, and I'm not using a reduction formula, I'm using a beta function. 6 is 18 is equal to, this is the integral 0 to pi by 2 sin raised to 4 theta and cos raised to 0 theta d theta. That is, here you can write here 1 by 2 beta 4 plus 1 by 2 means m plus 1 upon 2, here 5 by 2, and here cos is 0 means n is 0, 0 plus 1 upon 2 means 1 by 2. This is your answer. Now I'll explain here which formula you applied here. We applied here and check with different thing. Integral 0 to pi by 2 sin raised to m theta cos raised to n theta d theta can be written as 1 by 2 beta m plus 1 upon 2 m plus 1 upon 2, right here upon 2, and n plus 1 upon 2. This formula you applied here, and to get this one, here cos power is not there means cos, here n equal to 0, this n is equal to 0 and m equal to 4. 4 plus 1 is 5, 5 by 2 you got here, and here put n equal to 0, 0 plus 1 by 2 means here you get 1 by 2 answer. This is our beta m n, okay, beta m n. Like that you can solve any types of examples by using the standard substitution and the property with beta function and gamma function. We need to learn all these properties. I'll go from slide 1 to slide last one. Now this is your beta function formula. Beta mn equal to 0 to 1 x raised to m minus 1 1 minus x raised to n minus 1 dx. This is the main property you have to learn. After that you have to learn these properties. This is property conversion for the beta to gamma, and don't learn all this formula, only this formula you have to learn. I'll tick mark here. This is important, and the interest of this one you can learn this one and get all the formulas are merged with that examples and that properties. Now second one, these are the additional properties which I took. First example, integral a to b. If both limits are constant, and these limits are utilized into the factor form. Here a and b, here both the limits are utilized here as a factor form. Here b and here a, and here. And while taking this one substitution, let's like to take here these two difference into t plus a, then you get directly that formula. And this is most important formula, x raised to m minus 1 upon a plus b x raised to, this also a very important formula. This is also the, and these beta function formulas helps to you solve this. This is the one example which covers the a to b formula, and second example, this is your substitution method, converse cosine and sine power examples, and here this is examples which covers both beta function as well as gamma function also. And you can see this is the most important formula. That formula covers x raised to n upon a plus b x raised to m plus n formulas, and Like this, you can utilize these all the formulas to get the values. Now, we'll stop here for these lectures, and in next lectures we'll learn Davis rule.